Some types of polar equations come up commonly enough that it's good to be able to recognize their graphs from their equations. One type is r equals a plus or minus b times the sine of theta. Notice that we have two terms, one of which is a constant. This curve will take on certain shapes depending on the relative sizes of a and b. And while I've written it as the sine of theta, everything I'm going to say goes along with whether it be the sine of theta or the cosine of theta. Now, what I just said about the relative sizes of a and b, what I mean is that if the absolute value of a is equal to the absolute value of b, then the shape that we end up with is something called a cardioid. It is so named because the graph resembles a heart. This particular curve is r equals 3 minus 3 times the sine of theta. And you can see that when the sine of theta is equal to 1, we have 3 minus 3, and so we have a point at the pole because the radius is 0. When the sine of theta is equal to negative 1, we end up with 3 minus negative 3, and so 6. And so when theta is 3 pi over 2, we have a radius of 6. If the absolute value of a is greater than the absolute value of b, then we have something called a limacon. Why it's named limacon, I can't tell you. And in fact, this is a dimpled limacon. And you can see the little dimple here at the top of the curve, kind of like a cardioid, but it doesn't exactly touch the pole. The equation for this graph is r is equal to 3 minus 2 times the sine of theta. And so here we've got 3 as the constant term, and then 2 is the coefficient for the sine function, or really negative 2. And so we see that a is bigger than b. And the reason this will work out the way it is because when the sine function maxes out, we have 3 minus 2, which is 1, and so this graph will never touch the pole. When the sine function is negative 1, we have 3 plus 2, and so a radius of 5. Finally, if the absolute value of a is less than the absolute value of b, then we have something called a limacon with an inner loop. And so not only does the graph touch the pole, but it extends and we get this little loop inside. This graph came from the equation r is equal to 2 minus 3 times the sine of theta. So as you can see, when the sine of theta is equal to 1, we get 2 minus 3, which is a radius of negative 1, with an angle of pi over 2. And so along the line pi over 2, the radius is negative 1. We flip over the pole, and that's how we get the inner loop. And then when the sine of theta is negative 1, we have 2 plus 3, which is 5. And so that's kind of the maximum value we get. If any of these had been a cosine instead of a sine, then these would be, they would have symmetry with respect to, instead of the line theta equals pi over 2, they would have symmetry with respect to the polar axis. In other words, their graphs would appear rotated 90 degrees. So to sum up these ones, if a and b are the same in magnitude, we're going to touch the pole, and we have that cardioid shape. If a is in magnitude larger than b, we don't quite touch the pole, so we end up with a dimple. And if a is in magnitude less than b, then we end up with that loop. Another common type of polar equation is r is equal to a times the sine of n theta. Could also be the cosine of n theta. Again, that'll just affect the orientation of the curve. This one's a little interesting because it's a rose, and it has n petals if n is odd, and 2n petals if n is even. And this is what our rose looks like, kind of like a propeller. This one is the graph of r is equal to 4 times the sine of 3 theta. And that 3 theta corresponds to our 3 petals. The 4 is actually the maximum that the radius will be, because the sine function maxes out at 1, and so whatever that coefficient is, that tells me how far out, how long each petal is, essentially. If we were looking at the sine of 4 theta, then we would have 2n petals, and so there would be 8 petals. And anytime we have a rose with petals, these petals, oh, by the way, it's P-E-T-A-L-S, right? Not like a bicycle, but like a flower. Anyway, the tips of the petals are evenly distributed around the circle. And so for a rose with 3 petals, these 3 petals are 120 degrees apart at their tips. So what if n is equal to 1? Like, suppose we have r is equal to, we'll say 4 times the sine of theta. This up here tells me I would have one petal, but what does a rose with one petal look like? Well, if n equals 1, it looks like a circle. And you can verify this by actually taking this equation and converting it to rectangular form. Multiplying both sides by r, I get r squared is equal to 4r times the sine of theta. R squared is equal to x squared plus y squared. R sine theta is equal to y, so I get x squared plus y squared equals 4y. Completing the square on y will give us x squared plus the quantity of y minus 2 squared equals 4. And so what we see is this is a circle of radius 2, or diameter 4, right? And it has a center of 0, 2, and so halfway across the circle. Again, if this was cosine, the circle would actually be on the positive x-axis, the polar axis. A negative in front of the coefficient would just flip the circle around to the opposite side of whichever axis it's on. Now, sometimes folks get confused with it's n petals if n is odd. Wait a minute, was it 2n if it was odd, or if 2n if n is even? A way to remember this is, folks, if it was 2n if n was odd, and n if n was even, then no matter what, I'd have an even number of petals. That's not the case. And so I have to have an option where I have an odd number of petals, and so we double it when it's even. Now, having said that, look, they all have 2n petals. It just happens that when they're odd, they exactly align on top of each other, and so we only see, the odd number of them. If that didn't make sense, then plot them out. Theta is the input variable, r is the output variable. Put in various values for theta, see what the radii are, plot what you get, and you'll see that you'll trace over these 3 petals twice as theta goes from 0 to 2 pi. The last one we'll look at for the moment is called a lemniscate. It has the equation r squared equals a squared times the cosine of 2 theta, and it looks like an infinity symbol. I'm not sure how often it comes up, but I think it's kind of cool because it looks like an infinity symbol. In this case, this equation is r squared is equal to 4 times the cosine of 2 theta. And in this case also, if instead of the cosine it were the sine, instead of this being an infinity on its side, it would be rotated at a 45-degree angle.